So today I'm hoping to get to the first quantum algorithm, so it'll be an exciting day for us. But there are some other things that I have to do before I get to that point. At the tutorial session yesterday afternoon, I was asked a question about entanglement, and I did not give a satisfactory answer. So I would like to do better now. So that will be the first topic. We were talking about entanglement in the concept of 2 qubits. Of course, it's more general than that. So if I have 2 qubits and each is in a definite state, so qubit 1 is in a linear combination of 0 and 1 with coefficients A0 and A1. And qubit 2 is also in a definite state with coefficients B0 and B1. Then the overall state is just a direct product of these two. So it's the state qubit 1, the state for qubit 2. Temporarily on these, with this Dirac notation, I put a subscript 1 here just to make it clear that that refers to qubit 1 and this to qubit 2. But then when I combine everything, I will use the usual notation of not indicating that the first 0 here means qubit 1, the second 0 means qubit 2. We just assume we agree to that that's what it means. So then there's this linear combination of 4 states. And this is an example of a product state that you see from the line above. It's a product of the state of qubit 1 and qubit 2. Now this is not the most general 2 qubit state. It's some arbitrary linear combination of the 4 basis states, 0, 0, 0, 1, and so on. And that for a general state, let me call the coefficients C0, 0, C0, 1, etc. So if you compare this with this, you can see that if I take the product of the coefficient of 0, 0 and the coefficient of 1, 1 and multiply them together, that's A0, B0, A1, B1. That's exactly the same as the product of the coefficients of the 0, 1 and 1, 0 state. That's also A0, B0, A1, B1. So in a product state, the following condition is satisfied. C01, C10 is equal to C00, C11. This is a condition which must be satisfied for this to be a product state. If this condition is not satisfied, then we say that we have an entangled state. So, can we give a measure then of a quantitative measure of entanglement, something which we can compute for a given state, which would give 0 if this condition is satisfied, and something non-zero if it's not satisfied. And this is the Van Neumann entanglement entropy, which we'll now mention. So, yeah, it could be complex. I'm assuming the coefficients were real, but we haven't got there yet. But yes, one would be complex in general, but let's assume real coefficients here. So in general, one has a system, one divides it into 2 subsystems, A and B. So in our example, each subsystem is just a single qubit, but it's more general than that. And we write the state then as a sum over states of subsystem A, states of subsystem B. Let's label those by X and Y. And the amplitude of this particular state is CXY. That corresponds to here. So then one can compute. So the density matrix, say for subsystem A, is obtained by tracing out the effects of subsystem B. And it's defined by the XX prime element of the density matrix for A is obtained by the amplitude for A to be in state X and B to be in state Y times the amplitude for A to be in X prime times B to be also in Y summed over Y. So this tracing out the subsystem B. And as was pointed out, if these coefficients were complex, one of these should be a complex conjugate. So this is the density matrix, and one can get a quantitative measure of entanglement This is the von Neumann entanglement entropy, and this will be for subsystem A. So it's minus the trace of rho log rho. In general, rho is not diagonal, and we can write this in, so it's convenient if it's not diagonal to diagonalize it, and there will be eigenvalues lambda I. So this is lambda I log lambda I. This is rho A. Thank you. Yes. So I leave it then as an exercise to the student to consider the case of 2 qubits, and with a state like this, but where this constraint is satisfied, compute the von Neumann entanglement entropy by diagonalizing the 2 by 2 matrix for rho A and seeing that this gives 0. If we have not a product state, but an entangled state, such as one of the Bell states, the entanglement entropy will not be 0. So if you compare with this general state, only C0 naught and C11 are non-zero. So if you work out the, so rho A is a 2 by 2 matrix. If you work out the 0, 0 element, so this is the formula, so we're setting x equals x prime equals 0, only the term where y equals 0 contributes, and you get 1 over root 2 squared. If you do the same thing for the 1, 1, so x equals x prime equals 1, only the term where y equals 1 contributes, and that gives you the same thing. And you can trivially check that if you work out the off-diagonal elements, nothing contributes, and so you get 0. And so in this toy example of a Bell state, tracing out the second qubit, the density matrix for the first qubit is 1/2, 0, 0, 1/2. The sum of the diagonal elements add up to 1, as they must, because this is just summing the probabilities. And, but if I take the two eigenvalues of each are half, and so the entanglement entropy, each eigenvalue is the same, so there's a factor of 2, and then it's a half log a half, which is log 2. And for a system with 2 states, this is the maximum possible entanglement entropy. But one can have other partially entangled states where you can get an answer in between 0 and log 2. So as I say, the homework exercise is to show that for a product state which satisfies this condition, the entanglement entropy is 0. So why does it, you're saying the entropy is increasing, and why is that? And just off the top of my head, I can't give a clear answer to that. Let me think about that, and we can, at the end maybe. Interesting question. Okay. So as you were saying, the gates are reversible. So we have to think about reversible computing. And so, for example, the CNOT gate acts like this. We have two bits. The top bit, which is the the control qubit, stays the same, and the target qubit is the exclusive OR of X and Y, which is the same thing as addition modulo 2. Yeah, okay, right, yeah. Sorry, yes. So you're right. The entropy at the end is, the real entropy at the end is still 0, as you said. But by looking at this a subsystem, you can compute this von Neumann entanglement entropy, which is not, at least in this case, the real thermodynamic entropy of the system. Okay. So we represent then the sequence of gates by a circuit, and just to remind you, we read from left to right. So the upper qubit is acted on by a Hadamard gate, and then it goes, the two qubits go through this control NOT. So we read from left to right. That's the important order. And this is just reminding you of what we did last time, which is related to the question that was just asked. Sorry, yeah, okay. This is psi naught, say, and this is psi 1. So what is psi naught? Well, there's the state of the upper qubit, which has been acted on by the Hadamard, and the state of the lower qubit, y, that's unchanged. So that's y and x. These are states in the computational basis, and a 0 or 1. If we want to input states which are linear combinations, we have to work things out using linear superposition. So what's the action of a Hadamard on 0? I'm going through this again because it's really important we have this in our minds for what's going to follow. It's 1 over root 2, 0 plus 1. And h acting on 1 is 1 over root 2, 0 minus 1. So I can combine these two together. Hadamard acting on some state x, which is 0 or 1, is equal to 1 over root 2, 0 plus minus 1 to the x times 1. That combines both these two into a single formula. So this is what I have to put in here. 1 over root 2, 0 plus minus 1 to the x times 1. So the first state here is the target qubit, the upper one. The second state is the control qubit, which is the lower one. So what happens now when this linear combination goes through the CNOT gate? So we have to take each of these terms in the linear superposition separately. So now we're computing psi 1 after the CNOT gate. So when the control qubit is 0, the target qubit doesn't change. So we get 1 over root 2, 0, y. Whatever y was, it stays the same. And then the second term has a minus 1 to the x. And the target, the control qubit is 1. And then when the control qubit is 1, the target qubit flips. So we get y bar, the complement of y. So y bar is 1 minus y. And this is the 4 choices of x and y give you the 4 Bell states. If I take x equals y equals 0, we get the particular Bell state that I discussed just before in the context of the entanglement entropy. Okay, now we come to an important theorem. It's almost too trivial to be called a theorem, but it's important to think about in the context of quantum computing. So we have our system, and it's in some particular quantum state. Can I duplicate that state? Can I clone that state? Well, if this was classical, you could just look and see what the state is and then construct another one of the same sort. But you can't really do that with quantum mechanics, because if you do a measurement, in general, you change the state of the system. If in the basis in which you're doing the measurement, the state of the system is a linear superposition, when you do the measurement, after the measurement, the state will be in just one of those basis states, and which one will be given according to the usual probabilities. So in general, making a measurement changes the state. So is there any way, without measuring it to see what it is, we can clone a state? The answer is no. There's something called the no cloning theorem, which is, as we'll see, pretty obvious, and was presumably understood by the founding fathers of quantum mechanics, but for 50 years nobody thought it was really worth thinking about or even mentioning until people started talking about quantum computing. And then if you could clone a state, that would be extremely useful. So it's important to realize that you cannot. And this is a consequence of linearity. Okay, supposing then we had some operator or gate, U, some unitary operator, which, when acting on, well, there's 2 pieces to it. The original state is psi, and we want to copy it into some other set of qubits, which maybe initially we prepare in state 0. So this is the state we want to copy, and we want to copy it into this register here, which is in state 0, say, though there's nothing special about that. Supposing we could do that, and we've copied this, we've been able to duplicate it. Supposing we could do that. Then let's consider the same thing, but for a different state, phi, which we want to copy into this other register, which is initialized to 0. No. Supposing, at least for some psi and some phi, we could do that. So then, if we form a linear combination, this operator acting with the initial state is, say, A psi plus B phi. That's our corresponding to psi here. And we want to copy this into some register initialized to 0, then because of linearity, it's just the sum of acting with psi by itself multiplied by A. So that would be A, U, where we do try to copy psi, plus B, unitary operator, where we try to copy phi. So this is a trivial consequence of linearity. So we get A, psi, psi, plus B, phi, phi. So have we succeeded in cloning this linear superposition? Indeed, we have not. If we were to... But this is not a clone. So let's write a clone state would be where the first set register is in a linear combination of psi and phi, and the second one would be exactly the same. This is what we would like to do, but that's not what we had. If I expand this out, I get A squared psi psi plus AB psi phi plus B AB phi psi plus B squared phi phi. So this is not the same as this unless either A or B was 0. So unless A equals 0 or B equals 0, we not cloned. So this is a simple and pretty much obvious theorem, but which turns out to be important. Yeah. Well, I think for a general state, you cannot clone it. I don't think you can get very close to cloning it in general. I mean, if A and B were 1 over root 2, I don't think you could get close to cloning it. Maybe they're orthogonal, but in general, you could not do it. And we want something that will work in a general situation. I guess if they were orthogonal, you could do a measurement and pick out one or the other. I think that's the point. Okay. So before we go on to our first quantum algorithm, which is Deutsch's algorithm, we need to work a little bit more about these gates, in particular, the effects of these ubiquitous Hadamard gates. So let me just try to find this. Okay. So we remember that the X operator, that's like sigma X, it flips the bit, and Z changes the phase of the 1 basis state. This is like sigma Z. And we're considering then a control NOT. Now, I like at this point to write the control NOT to indicate that this flipping, which is done if the control bit is 1, is done by the operator X. This will be very useful in proving certain relationships. So let me write this control NOT with an X here. So this says if the control bit is 1, the target bit at the bottom gets acted on with X, which flips it. One can do other types of controlled operations too. In particular, we will consider a control Z, which is exactly the same thing. If the the control qubit is 1, then the target qubit at the bottom gets acted on with Z, which changes the sign of the piece of it involving basis state 1. So if the control bit is 0, nothing happens. So for 0, 0 and 0, 1 input, the right-hand states at the end are the same as the states at the beginning. If the control qubit is 1 and the target qubit is 0, then this target qubit 0 is acted on by Z, but when it's 0, it does nothing because we have +1 here. So also the 1, 0 state is unchanged by this. However, if both control and target qubits are equal to 1, because the control qubit is 1, the target qubit gets acted on by Z, and if it is in state 1, then because of the minus sign here, it changes the sign. So for the 1, 1 state, you multiply by -1. But notice this result then is completely symmetric between what I'm calling the control qubit and what I'm calling the target qubit. It's completely symmetric. I could write the control Z the other way around like this, and it has exactly the same effect as writing it like this. This will be the same. Because in both cases, all that happens, unless both inputs on the left are +1, nothing changes. And if both inputs on the left are +1, then the sign of the wave function changes at the end. Okay. So we've already said that 2 Hadamards multiplied together are the identity that's trivially seen. So if I have a circuit with H and H, I can just delete those 2 Hadamards because they give the identity. We showed in the last lecture that if I take an X and sandwich it between 2 Hadamards, that's a Z. So H, X, H I can replace by Z. And similarly, we showed sandwiching a Z between 2 Hadamards gives an X. So H, Z, H can be replaced by X. So what this is leading up to is to figure out so as I've emphasized that if I have a CNOT, which is equivalent to a CX gate, as I just said, call this X, this is little x, little y, this is little x, this is little x exclusive or y. These expressions are what you have for computational basis states put in on the left. And if you have linear combinations, then you have to figure out what you get on the right-hand side by superimposing all those linear combinations. So what I want to consider then is what happens, and this will turn out to be useful, if I sandwich Hadamards between the inputs and the outputs to a CNOT gate. And I feed in, say, X here and Y here. These are computational states, but these Hadamards on the left, they give us linear combinations of zeros and ones. And then the Hadamards on the right also transform linear combinations of zeros and ones. So the question is what do I get at the output? Okay, so that's what I've put here. This handout is on the website that I mentioned earlier. So you see, we have H, X, H. We know how we can simplify that. H, X, H, that's the same as a Z. So I can delete the two Hadamards on the lower line and replace this with a control Z. So that's using this equation 3 here. But now I know that the control Z is symmetric between the two bits, and so I can put the Z at the other end like this using equation 1. What happened then? So the control Z is symmetric, so I can put the Z at the other end. And then what is HZH? Well, we already had that from one of these formulae up above. That's just an X. So this control NOT gate with Hadamards at the beginning on the left and on the right is equivalent to a control NOT gate, but with the role of this is the control, and this is the target, with the role of the control target qubits interchanged. So if this is X and this is Y, the lower bit is unchanged. So this will be Y. And the upper one will have the exclusive OR of X and Y. So we will need these results in what's going to come a little bit later. I would say that it's not obvious that these Hadamards with the control NOT are equivalent to no Hadamards and the control NOT, but with the target and control bits interchanged, but it's true. You can derive this result in different ways. Each of these you can consider starting from some initial state. The direct product of two Hadamards is a 4x4 matrix. The control NOT is a 4x4 matrix. The two Hadamards is a 4x4 matrix. So you can figure out what those 4x4 matrices are. You can multiply them together, and you will end up with something equivalent to a control NOT, but with target and control bits interchanged. This, I think, is much easier than figuring out those 4x4 matrices and multiplying them together. Okay, so we have to get a little bit of experience with doing these sorts of manipulations. Okay. Now I don't think I need this anymore. I will put that up. Naturally, when we're doing computation, we need to be able to compute functions. Doing it on a quantum computer, the process, of course, has to be reversible. So every function we compute, there must be an inverse. We must be able to compute the inverse function. So what we do in this gate model to compute functions is the following. It's very similar to what we've been procedure. We have some input, which we'll denote by X, but this could be not just one bit. In general, it might be N qubits, say. The simplest case, and the one we'll do first, n will be 1. But generally it needn't be. And the output then is going to be some function f, which will depend on x, and that might have m qubits. As we've emphasized, in order that the procedure is reversible, we need to keep both sets of qubits, both in the initial state and the final state, in order that it can be reversible, invertible. So, because the point is, if f assigns the same value for different values of the input x, we can't invert the process because we don't know which of those x values to go back to. So the standard procedure will be the function f will be represented by some unitary transformation u. There will be an input register, which means a set of qubits, an input register in state x with n qubits, and there will be an output, or the second set of m qubits, which is going to contain information about the function eventually. But both registers, both sets of qubits have to be present in the initial state and the final state. And what that will give us, following along with what we've been doing with CNOT gates and things like that, this is a generalization, x, which is the input, will stay the same, but will still be preserved at the final state. And the output registers will contain the bitwise modulo 2 addition, or if you want, exclusive OR of y and the value of the function. And this will have m qubits. So this is reversible. Why is it reversible? Yes? So x is the input, but we're going to compute is a function f of x, where x is a string of bits and f will be a string of bits. Well, okay. Depending on the, okay, what should I choose initially for this, this register with m qubits? That will, typically it will just be 0. In many cases it will be 0, but in other cases it might be something different. Yes. Y is also specified with the incoming, with the initial state. So we specify the value of the argument of the function f and some second register with some other value in it, y, which will be chosen according to the function I'm calculating, and the output will preserve the input value x, and the function f will be encoded in this second set of registers. So where f of x is 1, whatever y was before it will be flipped. So if we act twice, we have to make sure that this is a unitary transformation, that there's an inverse. And so if we act twice, that is UF acting on this state, xn, exclusive OR of y and f of x with m qubits. And then if we do it again, we get x, and then the output registers will be y, exclusive OR f, exclusive OR f. So remember, this is bitwise addition modulo 2. And if I add a number to itself, a bit to itself, modulo 2, I always get 0. Because 0 plus 0 is 0. 1 plus 1 is 0 plus a carry bit, which we ignore because it's doing modulo 2. So this is the same thing as we started with. So if I act twice, I get the identity. So the process is reversible. Let me just draw this as a circuit diagram. I hope it will be clearer. There's some initial state, and there's an input register containing n qubits, and there's a so-called output register which will be initialized in some convenient way. If we want to indicate in the circuit diagram that this line is not 1 qubit, but is some different number, it's conventional to write a slash and the number of qubits that are involved. So this is n qubits, this is m qubits. There's some function here which would need to know how to compute. And the output, also the final state, y exclusive or f of x. And this is with m, this is with n. So we keep the input. That's essential in order to be able to reverse the process. And the information about the function, it comes from determining whether whatever initial value I put for y here, whether it got flipped or not. If it got flipped, f was 1, and if it didn't get flipped, f was 0. So the notation, I think, is a little confusing. One often talks about this upper set of bits as the input because it contains the input x, and this lower one as set as the output because it contains information about the function f of x. But actually they're both present, both in the initial state and the final state. Okay. One final thing before we discuss our first quantum algorithm. We have mentioned earlier about universality of universal set of gates. And I'm just going to reiterate that without proof. If you want proof, you go to Nielsen and Chung. And so quantum mechanics, so universal quantum gates. So the statement is that we can approximate any unitary transformation with arbitrary precision with the following set of gates. We need a CNOT gate. This is the only 2-qubit gate we actually need to be able to do universal quantum computation. And needless to say, the Hadamard. And 2 other gates, S, basically S changes the phase of the one basis state not by -1, which was what Z would do, but by I. And T is the same thing, but it changes it by pi over 4. You will see that s is just t squared, so it's sort of redundant to include s, but it's often convenient it's a convenient gate to have. And the z operator is, of course, just s squared. So we don't need much. We need CNOT and h, and really just this one. Now, unitary transformations depend on continuous sets of parameters, and if you want to specify the transformation with some high precision, you're going to need a very complicated set of these gates to get that high precision. If it was some phase by some angle which isn't sort of pi by 4 or something simple. But the claim is you can get, if you're willing to have a complicated enough circuit, you can represent any unitary transformation to arbitrary precision by combining these gates. So sometimes restricting yourself to 1 and qubit gates might involve a very large number, and sometimes a 3-bit gate like the Thutupalli gate, so-called, can be useful. So since you often hear about Thutupalli gates in the context of quantum computing, let me just tell you what it is. So it's a 3-bit gate, so we have 3 in the initial state. Two of the bits x and y, these are control bits. And the third one is the target qubit, and the target qubit flips if both x and y are 1. Right? That's what this means. So nothing happens unless both target qubits x and y are 1, and if that is the case, then the control qubit flips. Okay. So it's often convenient to use Thutupalli gates, though this can be replaced by some sequence of these other gates, 1 and 2 qubit gates. Okay. So I think we've done enough preliminaries now to start with our first and relatively simple quantum algorithm. So just so you know where we're going, I'm going to describe 3 quantum algorithms. The first one is due to Deutsch, 1985. Along with Feynman's 1982 paper talking about quantum simulations, these 2 papers are considered the 2 that really got started the field of quantum computing. So this will be a toy model. So it just involves 1 qubit, input and output. And the quantum speedup will be a factor of 2. Not very spectacular. The second will be Simon's problem. It's like the Deutsch problem in the sense that it's of no practical interest. But, and this should make you pay attention, it gives an exponential quantum speedup, exponential in the size of the problem. Exponential in problem size. So, potentially then you can have exponential speedup. This is a problem of no practical interest, is it possible then to find a problem which is of real practical interest and which you can give you a quantum speed up? And the answer is yes. And this is going to be the high point of this course, which is Shor's algorithm for factoring integers, which is an extremely important problem, as I will explain. So this is exponential speedup for a problem of practical importance. So this is so you know where we'll be going in this lecture, and certainly the next one, if not the one after that. It's Shor's algorithm that transformed quantum computing from an arcane field of interest to a handful of physicists to a huge field of interest not only to physicists, but to engineers, to industry, to the government, to the military, and lots of funding going with it. So this is the plan, so you'll know where we're going. So first of all then, Deutsch's algorithm. What I'm going to do is, which is the usual thing, is give a somewhat improved version of Deutsch's algorithm. The version originally published only worked half the time, but a simple change means it works every time, and that's what we're going to discuss. Okay. Yes, they're distinguishable. They're different, say, superconducting loops. Yes, they are distinguishable. So if the quantum objects are confined in different regions of space, they're distinguishable. If I know there's one electron in this box in state 1, there's an electron in that box in state 2, then I know that the one in this box is 1 and that one is 2. No? Whoops. What's happened to my notes here? Okay. So we're going to consider a toss of a coin. We want to know if this coin toss is fair or not. If one side is heads and the other side is tails, that's what I'll call a fair coin toss. But if both sides are heads, that's what I would call an unfair coin toss. How can I tell whether the coin is fair or not? Well, you have to pick it up. You look at one side, and you look at the other side. You have to do two operations. In terms of putting this in a mathematical formulation, let's say that X is the refers to the top side and the bottom side. So these are the two possibilities. X equals 0, say, is top side. X equals 1 is bottom side. And so it's a function of one bit. And we compute the function then is either heads or tails. And say heads is 0 and tails is 1. So f of x, so x is 0 or 1, and f of x is 0 or 1. So what we want to know then, in language of mathematics rather than coin tossing, is f of x constant? That is to say, f of 0 equals f of 1. Both sides of the coin are the same. This is cheating. Or f of x not constant, but the word balanced is often used. So f of 0 is different from f of 1. So in mathematical terms, this is how we would represent the coin toss. So in mathematical terms then, how will we distinguish whether the function is constant or balanced? Well, you take x equals 0 and you compute the value of the function. Then you take x equals 1 and compute the value of the function and say, are they the same? You've got to compute the function twice. With this quantum algorithm, we will be able to answer this particular question, whether the function is constant or balanced, by a single application of the function. This is possible, of course, because of quantum parallelism. We will be simultaneously, with one application of the function, working it out for both values of x equals 0 and x equals 1. When we do a measurement, we will not be able to determine separately what f of 0 and f of 1 are, but if we restrict ourselves to this more limited question, we will be able to answer this question with one call to the function. And the key will be these Hadamard gates again. So what are possible values for these functions? So there's 2 values of x and 2 values of f, so there's 4 possible functions. So let me call them f1, f2, f3, f4. And they will give, they're different depending on the values for when they're computed for x equals 0 and x equals 1. So f1 will say give 0 for both arguments. This is a constant function. f2, say, will give 0 if x equals 0 and 1 if x equals 1. This is not constant, this is balanced. Similarly, f3, which is 1 for x equals 0 and 0 for x equals 1, is also a balanced function. And f4 gives 1 for both arguments, and that's a constant. So if I have a black box which has this function in it, and I would like to know information about the function with just one call to the function. So here's our black box. Unitary transformation representing a function. And there will be an initial state and a final state with x and some value y, and the output will be, the final state will be x and y exclusive or f of x. So to determine whether f is 0 or 1, we see whether the lower qubit, whether it did not flip or whether it did flip. All right. So for each of these 4 functions, let's represent them by a quantum circuit. All right, so we start here. So F1, okay, so this is going to be U, F for the first function. So we now, if the function is always 0, no matter what, this is F1, y doesn't flip. In no case does x flip, so nothing happens. So this is our circuit, F1. Remember, that corresponds to F0 equals 0 and F1 1 equals 0. Now for F2, so x stays the same, but now if x is 1, f1 is 1, and therefore, and therefore y has to flip. So if x is 1 making y flip, that's just our CNOT gate, which I'll write with an X here. So the output here is y if x equals 0, and the complement of y, the flipped y, if x equals 1. That's because of the controlled NOT or controlled x there. So if, and this is f0 equals 0, f1, we already said that, sorry. So this means you flip y. So if we continue on, let's go over here. The third function, f3, is x. Now, it's like f2, except it's the other way around. Y flips if x equals 0, not if x is equal to 1. And I can get that if I insert an extra flip for y before this control NOT gate. We'll discuss that, y. So we flip y, and then we do the control NOT. So x stays the same. Now, supposing x equals 0, then y flips because of this x gate. It doesn't flip with the control NOT because x is 0, the target, the control qubit is 0, so you get the complement if x is equal to 0, and if x is equal to 1, then this control NOT flips y, so it gets flipped twice, and it comes back to what it was before. And this is for f0 equals 1, f1 equals 0. And for the fourth possible function, the last one, whatever the input is, the output is 1. So I don't care what x is, I just flip y. So these are, in circuit representations, the 4 possible functions. And we're going to, by adding Hadamard gates in front and after these functions, we will be able to tell whether the function is constant or balanced. Now, I should mention the usual ways the books describe this is to work through what is the wave function at each stage. Personally, I find it easier to use these circuit diagrams and identities for circuit diagrams. Once you get used to it, I think it's easier. So, we're going to sandwich the UFs between Hadamards. Okay, so this is what we're going to do. We're going to have an input will be x, x, y. So we're going to have a Hadamard. We're going to have our function. We're going to have a Hadamard, and then we're going to see what we get. And I should mention, now, I was asked before, what do you choose for Y, for this auxiliary second register? Here we're going to choose it to be 1. That's the desirable choice for what we want to do. And we want to know for each of the 4 functions, what do we get here? And we'll see that from the output, we will unambiguously be able to say whether the function is constant or balanced. We will not be able to determine separately the 2 values of the function, but we will be able to say whether it's constant or balanced. I want to keep those. Okay, so F1. So if our black box is F1, then actually there's nothing in it. It just goes straight through. So we have just, and I should mention, maybe I should make this clear. What we're going to do at the end then is put here a measurement gate. We do a measurement. Of course, at some point we have to do the measurement, and this measurement will tell us unambiguously whether the function is constant or balanced, depending upon whether x flipped or not, basically. Okay, so for F1, on the upper qubits x, and we just have a Hadamard, and then another Hadamard, and then we have our measuring gate, and then for y, Hadamard, this was 1, sorry, the low one was 1, and then we know, well, that's certainly going to, and then, okay. So we know that the 2 Hadamards just give the identity. So what we get out from the upper register is just x, and from the lower register is 1. So maybe we will make a list somewhere. The different outputs. So for F1, the measurement is we get x and we get 1. And this is for F0 equals 0, F1 equals 0. This is constant. So what about the function F2? So we start again with x in the upper register, 1 in the lower register. We have an h, and we have an h, and then what do we have for F2? This was F2. It's just a control NOT. And then we do the measurement. So this is equivalent to, this was the exercise we just went through. This is is equivalent to having a control NOT, but where you exchange the control and target bits. So in other words, this is equivalent to, we just showed that, this is x, and this is 1. So the reason I set the lower register to be 1 is that this will then flip x. So this is x bar, and this is unchanged as 1. So where is my summary, F2, we get x bar, the complement of x. Whatever I put in for x, it gets flipped, and 1 stays the same. And this is for F0 equals 0, F1 equals 1, and this is balanced. So notice for the constant case, I get x. For the balanced case, I get the complement of x. And this is going to continue. What about F3? Where was F3? Hope I haven't rubbed it out. No, it's over here. Okay, so for F3, again, we start with x and 1, and I put in a Hadamard, and then what is there up there? Just the control, and a Hadamard, and then here we have the h. No, there was another x, wasn't there? Okay, so let me write this out better. This is the most complicated one. There's an h, and then from over there, there's an x, and then there's a control x, and then there's a Hadamard. Okay. So what we're going to do is insert here 2 factors of h, which correspond to the identity. So if I just redraw the lower one, we get h x h h x h. So h x h is just z. And this h x h is also just z. So this is equivalent to, so we go to this stage here, x we have h, h, and now this is a z, and we have another z here, and this is 1, and you will recall then that one can flip the order of the control bit and the target bit for z. So we can write this, I should write it out again. H, Z, H. And there's a Z there, and this is 1. And H, Z, H, this is equivalent to X. And this is 1, and we have a Z, Okay, so now we can figure out what we're going to get. No, that was what I didn't want to do. Shoot. X. So, this lower bit is 1. The z keeps it as 1, but just changes the sign of it. So with this control x bit, with the control bit being 1, x gets flipped. So this is x bar. And the lower one is just minus the state 1, the minus coming from the z operator here. So F3 is x bar 1, negative of that. And this is for F0 equals 0, F1, F equals 1, F1 equals 0, and this is balanced. And I think this has gone on long enough, so I'm just going to tell you, if you repeat the same thing for the fourth function, this is F4, that what you get is X, not X bar, and it's flipped in sign. So that's another simple exercise for the student. F0 equals 1, F1 equals 1, and this is constant. So by sandwiching Hadamards before and after this function and feeding an input where the lower qubit has value 1, we can tell whether the function is constant or balanced. If x, whatever I put for x, does not flip, it's constant. F1 and F4. If whatever I put for x flips, then it's balanced. F2 or F3. We did this with just one call to the function. Because of quantum parallelism, it's evaluating the function for both values of its argument, but in order to get some useful information when we do a measurement, we have to do some pre-processing with these Hadamards and post-processing also with these Hadamards. And if we do that, we can get useful information about the function. Namely, we can tell whether it's constant or balanced. We can't tell the two values of the function independently. So supposing, for example, I saw that x did not flip. So it is a constant function. It's either f1 or f4. Now, the wave function that came out is not exactly the same, but the two wave functions, for f1 and f4, just differ by a minus sign and an overall sign or phase. And when you do the measurement, you don't determine the sign of the wave function. So doing the measurement, you cannot distinguish between this state and this state, or similarly between this or this. So you don't know individually the values of the function for the two arguments, but you can answer this other question of whether it's constant or balanced with one call to the function. But we put it now, we are putting Hadamards in front and we're figuring out what we're going to get. And I thought I'd gone on long enough, and I'm leaving that as an exercise for the students. And I'm claiming that this is what you get. That x does not flip, and the state, the lower qubit changes sign to be -1. Okay. So it's interesting that in this case, you can use quantum parallelism to gain an advantage classically. It's, of course, a toy model. It's a small model. It's not of any particular interest. But it is interesting that you, conceptually, that you can gain by quantum parallelism. And in the next algorithm, which we're going to do, which I think I will defer to the next lecture, Simon's algorithm, it'll still be an artificial problem, but it will give us a spectacular quantum speedup by using quantum parallelism. X will give a speedup which is exponential in the size of the problem. But I think I'm going to stop now and start from afresh with that problem tomorrow.
So our goal here was to put in 2 qubits and find out whether they are equal or not.
Say this again, please.
Our goal with this algorithm was to compare 2 qubits and find out...
Well, the goal was to determine whether the function is a constant function or a balanced function. Okay. And we do that by this, in this Deutsch algorithm, we have 2 qubits go in, 2 qubits come out, and we see if the first qubit flipped or not. and the second qubit is set to be 1.
Questions? Okay, so if there are no other questions, so we break for lunch and meet at 2:30.
I have to unwind you.